So what the plan is for today, we're going to continue on AC analysis. Basically, we started talking about storage elements. We started talking about capacitors, inductors. We learned about the IV relationship between like those elements. And then we said, like, if we have any circuit that has like those elements in it, KVLs and KCLs still hold, right? So we can write KVLs, KCLs, do like mesh analysis, node analysis, all those techniques that we learned, we can still apply. What we're going to be doing today, we're going to look at two very simple examples, which we call them like first order circuits. And first order circuits are basically circuits that have only a single storage element. It's either like a capacitor or an inductor, but whatever it is, there's only one of them. And if there is like more than one of them, I got to be able to simplify it down into one, right? So we're going to start analyzing the circuits. And since they only have one storage element, we call them like first order circuits. And then we're going to justify why we're calling them like first order circuits. And later on, we're going to like, make it a little bit like more complicated. And we're going to have both like capacitors and inductors in the circuit. And since it has like both storage elements, we call them like a second order circuits, right? We're going to learn that we're going to have to like solve differential equations to be able to like solve and analyze those circuits. So before we get to like analysis, we're going to go over like differential equations to just make sure that we all know how to solve differential equations. Okay. So let me quickly review whatever we talked so far. So review. So far we learned about three different elements. We learned about resistors, we learned about capacitors, and we learned about inductors. And we learned about the IV relationship of like all these elements. And we also talked about this DC steady state conditions for these elements. And when I'm talking about like DC steady state, what I mean is that like what if current or voltage across these elements are constant and they're not changing over time, right? We talked about it. So let me quickly like summarize like what we have. So let's just say this is the element. This is the VI relationship. This is the IV relationship. And this is the DC steady state condition, right? So the first element that we have is a resistor, which we know the relationship between V and I is through Ohm's law, right? So if I have voltage across the resistor VR as a function of T, that is R times I through it, right? We talk about Ohm's law a lot, and that I did not matter to be DC or AC, right? If the VI relationship between, basically for a resistor, is through this formula, since it's an affine function, I know exactly what the relationship between I and V is. So I R of T is VR of T divided by R. And if my voltage or current, or both of them, are constant, again, I still have like this relationship, right? Ohm's law still holds. So if I'm in a DC condition, I'm going to show them with like capitals. So I have V equals R times I, right? This V and this I, they're constants, right? They're not changing over time. That's why I'm showing it with like capitals, right? But we know like Ohm's law holds regardless of the type of voltage and current we have. The next element we have is a capacitor. We know the IV relationship for a capacitor is through a derivative. So we know IC of T equals C dVc dt. And since this relationship is linear, we can find the inverse of it. And we know the inverse for derivative is integral. So I know the VI relationship. So voltage across the capacitor equals 1 over C, integral from minus infinity to T, IC of tau d tau. We also talked about what happens if voltage across a capacitor is constant. What's happening if voltage across a capacitor is constant? It means current through it must be 0, which means we have an open circuit, right? So the DC state means when voltage is constant, this results in current through it being 0, which is the same as open circuit, right? So as soon as I go from like time varying to constant, I have this steady state condition, right? The last element we talked about was inductors. We know the relationship between V and I for an inductor is through a derivative. So if I have voltage across the capacitor, the inductor VL of t, that is L dilt dt. Again, this is a linear operator, so I can find the IV relationship, which is going to be through integral. So IL of t is 1 over L integral from minus infinity to t, VL of tau d tau. Right? We'll talk about these. And what happens if current through the inductor is constant? As soon as current through it is constant, it means the derivative of it is 0, which means voltage across it must be 0, which is similar to saying we have a short circuit, right? So constant current means voltage must be 0, which is a short circuit, right? We also talked about the duality between the capacitors and inductors. So there is a duality between capacitors and inductors. By that, what I mean is that if I change the role of C by L or L by C, change VC of t to IL of t and IC of t to VL of t. If I'm given one set of equation, for example, for capacitor, I can obtain that set of equation for the inductor just by replacing C by L, VC by IL, and IC by VL. In this sense, we have like duality. For example, if I look at this IC of t, which is C dV C dt, if I change IC by VL, C by L, and VC by IL, I exactly get this equation, right? And it's true for every other equation that we have. So in that sense, there is a duality there, right? We also talk about something else. We talked about voltage across capacitor being continuous. We said since voltage across capacitor is written in terms of integral, it must be continuous. And if I use this duality, what it tells me is that current through the inductor must be continuous, which is true. Because we could write current through inductor in terms of an integral, which tells us it is continuous. So quick remark. Voltage across a capacitor, VC of t, and current through an inductor IL of t are continuous functions. And since these are continuous functions, when I'm writing my KVLs and KCLs, I prefer to write them in terms of either IL or VC, because these are continuous functions. It makes my life much, much easier, right? So these are the things that we talked about before, right? But let's just assume a scenario that I have a circuit that only has like one of these storage elements. And there is only one of them. We call this circuit a first order circuit. So let me quickly define a first order circuit. Definition: a first order circuit is a circuit that has a single storage element. This storage element can be either like capacitor or inductor, right? So capacitor or inductor. It doesn't talk about like how many resistors we have. It doesn't talk about like how many dependent sources we have or like independent sources we have. We can have as many as we want. What determines the order of a circuit is the number of storage elements that we have. If there is one of them in the circuit, we call it the first order, right? Is that clear why we call this the first order? Because there is only one storage element. And the reason that it's called a first order circuit is that when we're writing the KVLs and KCLs, we're going to have to end up solving a first order differential equation. Because remember, the relationship between V and I is through derivative, right? So if I write the KVLs and KCLs, I'm going to end up getting a first order differential equation, and hence the name first order, right? So let me quickly write that down. Remark: we can still write KVLs and KCLs. And the reason we can do this, because like KVL and KCL, there were basically equations that had something to do with the voltage and current and not the elements itself, right? So they still hold. So I can still write KVL and KCL to solve for currents or voltages in the circuit. Doing so results in a first order differential equation, and hence the name first order circuit. Right? And obviously, if you have like two storage elements, we're going to end up getting a second order differential equation, and we call it like a second order circuit. But for now, let's only focus on the first order circuits, which we only have one storage element, right? Here's a very important thing. Since voltage across the capacitor and current through inductor, they're continuous functions. So when we're given a circuit with like one of these elements, let's just say capacitor, we try to write down this equation, this differential equation, in terms of voltage across capacitor, because it's continuous and makes our lives easier. If I have a circuit that has like an inductor in it, I know current through inductor is continuous. Therefore, I try to write a differential equation all in terms of I through inductor. right? So remark, since voltage across a capacitor is continuous, to solve a circuit with a single capacitor, we write differential equation in terms of voltage across capacitor. And if we have an inductor, since current through an inductor is continuous, to solve a circuit with a single inductor, we write a differential equation in terms of current through the inductor. Right? Does that make sense? What's happening? Now we got the definitions out of the way. Let's talk about a circuit that has a resistor and a capacitor, right? Basically, let's talk about like RC circuits as our first order circuit. I'm going to claim the circuit that I'm about to draw is the most general RC circuit that it can possibly get. Let's see why. So